Our textbook states, and I'm talking about the Introduction to Analysis textbook, on page 98, you can see that it says, let f be a real valued function on an open subset U of R. Let x naught be an element of U. We say that f is differentiable at x naught if limit as x approaches x naught, f of x minus f of x naught over x minus x naught exists. If it exists, this limit, often denoted as f prime x naught, is called the derivative of f at x naught. So I just quickly wanted to demonstrate what this means graphically. So I already have a graph here, and I have my 2 points, x naught and x. So if we're trying to figure out the definition of the derivative here, we're basically trying to figure out what the slope is at this point x naught, because definition is just the slope of the tangent lines. So if we have this secant line, I'm going to start by pretty much just using the regular slope formula that we know. So x2 minus x1. So in this case, it would be f of x is our x2, and then minus f of x naught over x minus x naught. Okay, so we have the slope, but if we're thinking about this, we don't want a secant line, we want a tangent line at x naught. So if we got x to get closer and closer to x naught, eventually we would start seeing that we would get a tangent line at x naught. So how do we do this? Well, we take the limit as x approaches x naught, and this would give us that tangent line. So this is basically how we arrive at the definition. I just wanted to show what that would look like graphically. So why is the definition so important? Well, derivatives are used in many other subjects, not just in math. So we see it a lot in physics, also in engineering. And then using the definition of a derivative, we can develop a proof for the product rule, the quotient rule, chain rule, etc. And these rules we already know are shortcuts to taking the derivative, which makes our life a lot easier. We are going to go ahead and prove the quotient rule using the definition of a derivative. So let me just write down what I'm trying to show. And we have f prime So this we know is the quotient rule. So now my proof is going to start with basically plugging this in to the definition that I just stated above. So we have limit as h approaches 0. So if we plug that in, so we got f x plus h over g x plus h minus, and then it would be f of x over g of x. And then as h approaches 0, so at the bottom we just have h. So let's condense this a little bit. So limit as h approaches 0. And then I'm just going to find a common denominator here between these two. So if we do, let's see, g of x, f of x plus h minus gx plus h times f of x over, and now we go ahead and have that common denominator between them. And this is all over h. So I have this huge fraction here. So I'm actually going to simplify this. So these are going to be at the top. These two are at the bottom. So I'm going to have the limit as h approaches 0. And I'm actually going to separate these two here. So I'm going to put the 1 over h here on the side. And then that way I would have g of x, fx plus h minus f of x, gx plus h. Okay, and then I have this all over gx plus h times g of x. Okay, so I have this. All right, now from here, basically I can add in, let's go 1 over h. So I'm going to keep this first part here, h, and then I'm actually going to do minus g of x times f of x, and then I'm going to add g of x times f of x. So basically that just cancels out, so I'm not changing the equality, and I'm going to bring everything else down. So I have this, and this is all over gx plus h g of x. Okay, so I have this. All right, now from here, I'm actually going to switch my denominators, which doesn't change anything either. So I'm going to go, this is going to be 1 over g of x plus h times g of x. And this is going to be, so I'm going to change the h over here. So fx plus h minus g of x f of x plus g of x f of x. So this is one long problem. X g x plus h. And I'm changing the denominator, so now this is over h. Okay, so you're already starting to see the g squared right here in this area, but we'll keep going. So from here, we can actually start to pull out some of these variables, some of these functions, I mean. So we can pull out a g of x and a negative f of x. So if we do that, we'll get g of x here. And if I take out g of x from the top, I'm actually going to split these up into two fractions here. So the first one's going to be fx plus h. If I factored out that g of x, I'm going to have minus f of x over h. So that's going to be first fraction, and then I'm separating them. So the next one's going to be, if I pull out an f of x, so times, and then here would now be gx plus h minus g of x over h. Okay. So we have this, and properties of limits actually let me rewrite this as the limit as h approaches 0, x plus h g x. Actually, let me write this also separate. So that have limit h approaches 0, 1 over g of x. So I'm separating all of these, and then I'm going to have the limit which approaches 0, and then of g of x, and then the limit as h approaches 0 of fx plus h minus f of x over h. And again, this is going to be one long problem, so minus the limit as h approaches 0 of f of x times the limit as h approaches 0, almost done, of gx plus h minus g of x over h. So I have this, and now we can start seeing that these are actually the definition, using the definition of a derivative. So these are actually f prime of x, and this one is g prime of x. So we can already see it all coming together now. So we have 1 over gx squared, so that's these two here, okay, times g of x, that's this guy here, and then times f prime of x, that's that one, minus, and then I have f of x times g prime of x. So as you see, this is the definition of, this is the quotient rule. So I have this g of x times f prime of x minus f of x times g prime of x over g of x squared. So we arrive at what we wanted to prove. So this is the quotient rule. So we use this a lot to kind of shorten up taking up the derivative. Instead of using the definition every time you have a giant fraction, you use this shortcut. Makes your life a lot simpler. Okay, so another common application is the power rule, and I will be proving that one using the definition of a derivative. So this is what I plan on showing. So show that f of x is equal to x to the power n, and then f prime of x is equal to n x n minus 1. Okay, so the proof is actually going to use another form of the definition. So the form that I'm going to be using is f prime of a is equal to the limit as x approaches a, f of x minus f of a is equal to x minus a. So if we plug this in, if we plug our function in, so we get limit as x approaches a, and then we'll get xn minus an over x minus a. Okay, so basically we need to break down this right here. So xn minus an is equal to, and I'm actually going to pull out x minus a from this. So if we do that, then on the inside over here, we're going to get xn minus a plus a xn minus 2 plus a squared xn minus 3 plus, and then dot dot dot, so plus a n minus 2 times x plus a n minus 1. So we get this. Now if we plug that into what we have here, we would get limit as x approaches a, and then we would have this guy, so x minus a, and I'm going to shorten all this a little bit because it's just way too long for me to write each time, plus ax n minus 2 plus dot 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 plus, and I'm just going to put the last term, so n minus a. Okay, and this is all over this guy here, so x minus a is also at the bottom. So as you can see right away, these were going to cancel out. So really we have the limit as x approaches a of just this guy here. So if we just plug in a in for x, so then we're going to get a n minus 1 plus a times a n minus 2 plus dot 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 plus a n minus 1. Okay. And then from here, we know we have n terms because it starts at x n minus 1 and it ends with x to the 0 power over here. So there's n terms, and if you notice, each one of these has, if you add these two, you get n minus 1, this one's n minus 1, this one's also n minus 1. So really what we have, this is equal to n times a n minus 1. So we end up with f prime of a is equal to n minus 1. Okay, so from here, if we just plug in x in for a, we end up with f prime of x is equal to nx n minus 1. So this is here the power rule. So we end up with what we wanted to prove. So this is very commonly used if you're trying to, if you have a function x squared, instead of using the definition of a derivative, that would be very tedious. You can just use the power rule and know right away that this is just 2x instead of having to plug it into the definition every single time. So it saves up a lot of time, and so does the quotient rule, which is the other one we proved. So that pretty much concludes my presentation. These are the sources. This is just the textbook, and this is a really great source that I found for the proofs. And yeah, that was it. So thank you very much.